to moving forward in a spirit of reconciliation and working together in the science of astronomy. And with that, I would like to now introduce our first speaker of the evening for our beginner session, Gord Tulloch, who, when he's not building or destroying and then rebuilding an observatory or whatever the thing may be, tonight he's going to talk to us about, oh, it's all covered up. Just a second. There. How do we know that? Please welcome Gord Tulloch.
So I brought along a visual aid. Are we allowed to do that? Okay, wash your hands afterwards. Don't touch your mouths before you guys. This is a spectroscope. It's probably older than some people in the room, but it still works. The secret is this aperture is where the light goes in, and it actually projects the spectrum on this side, so you would have to look at something like this and then kind of go look at the side. So it's something to play with when you get bored. If you get bored. Of course, I've got like 22 slides, so we're going to be looking. So this is me. This is your obligatory cat picture. My AAVSO tag is TGR, which makes it convenient. And I also have a little observatory, which you've probably seen. So this presentation, when I was in introductory astronomy, maybe not quite in this room, but close, one of the things I found fascinating was I found out how we know stuff that I never knew before. How do we know how much a star weighs? How do we know what the temperature of a star is? Because we can't touch it, can we? So can we touch a star? Not really, not more than once. We can get close, and we have some probes that are doing that. But how do we learn about stuff that we can't touch? And especially, how do we know so much? How can we say with such confidence that this star is 4,229 Kelvin? Really? And what do we say when somebody says, as happens a lot these days, I don't believe you? Like, were you there? Right? So, how hot is it? What's it made of? How far away is it? How big and heavy is it? What orbits it? The answer is we can tell a lot from the light that we see, which is basically all we got anyway. So we've got to do the best we can. Am I being too loud? No? Okay. Okay. I sound good myself. So what is light? Well, Isaac Newton helped us out with this, and he'll be a recurring theme in this presentation. Isaac Newton may have not have been the first, but he was one of the first people to actually try to figure out what light is all about, and wrote a book on optics about how light reacts, how it reflects, how it refracts, what diffraction is, all that kind of stuff. And the thing he discovered, which was interesting, is when you shine light, white light, like sunlight, through a prism, it spreads the light out into its component parts. He discovered light is made up of a whole bunch of colors. We call that color, those colors, the spectrum, right? And we've also discovered that the visual spectrum, which is the pretty colors we see, is actually a very small part of an overall spectrum. So rainbows are just raindrops that are acting like prisms. And the prism is spreading the sunlight out into its component colors, so what you see is a pretty rainbow. What's actually happening from a physics point of view is that photons are hitting electrons and causing those electrons to become more energetic. They're popping up to a different energy level, and then, since they don't like being at that energy level, they pop down back to their original energy and re-emit that photon at a certain frequency. Depending on the material it is, it will emit at a very specific frequency. So that's how we can tell what things are made of. So, three kinds of spectrums that you have to think about. One is a continuous spectrum. It's also called a black body spectrum. If we had a piece of steel, or a stick, or a computer, At rest, it's not really emitting a lot of radiation, so we call it a black body. If you start applying heat to it, you start shooting infrared photons at it, it starts to get hot. So you got a piece of steel and you start heating it up. What happens? It starts to emit radiation and start giving that back to you. It starts out as very low frequency radiation, infrared heat. But eventually it gets hot enough that it starts emitting red light. So the iron gets red hot. Right? Then as you heat it more, it gets hotter and hotter. Does it get green hot? No. Because red and yellow and green does not make green. It makes something that looks a little whiter. Eventually it gets white hot because it's emitting across the entire spectrum. Right? White light is made up of all the colors. And eventually it'll start emitting in the ultraviolet and the very high frequencies. Right? Now, hot gas, on the other hand, as opposed to a black body, think of neon, for example. That's a gas. When you heat it up, it emits a light at a certain color. Right? So it's emitting at a very specific frequency. And what we see is we see these colored lines in the spectrum, called an emission spectrum.
Recording in progress.
Yay. Got it. So, we also, oops, I need to do that, right? Okay. There it is. Okay, so if we actually pass a continuous spectrum through cold gas, that cold gas, we're actually exciting the atoms in that cold gas, and it's taking up some of those electrons, or those photons, I should say. And we'll see gas in the spectrum at specific wavelengths where it's taking it up. And this is the kind of spectrum you'll see from stars, where the hot surface of the star is passed through a cooler gas in its atmosphere, and which is absorbing some of its light. So from the sun, you'll actually see a continuous spectrum with a whole bunch of dark lines in it. Right? Doesn't really matter if it's an emission spectrum or an absorption spectrum. Depending where the lines are, we can figure out where stuff is. As a matter of fact, in some cases, like a BE star, which is a very energetic star with a ring, almost like an accretion disk around it, a very hot gas, you'll look at one of the lines on its spectrum, and it'll be two peaks and then a valley, because it's actually the emission line of the bright ring and the absorption line of the atmosphere of the star. A BE star is got a very interesting spectrum. So, what does it tell us? Well, we know, because we can put hydrogen gas in a Bunsen burner and see what it gives us, right? So we know, for example, that hydrogen has some very specific lines. And sometimes we hear about them because we have filters in astronomy to filter out very specific wavelengths of light. For hydrogen alpha, for example, is what we look at the sun in. For the Balmer series of lines that is emitted by hydrogen, you've also got hydrogen beta, hydrogen gamma, hydrogen delta. All of these lines are very characteristic of the element hydrogen, right? Hydrogen is the simplest element. It has a lot of lines. One element that we can talk about, titanium oxide, has about 9,000 different discrete lines that it shows in the spectrum before you can figure out that it's titanium oxide. And yes, we do see titanium oxide, as you see. So what do we see? Energy is not spread equally in the spectrum. There are peaks and valleys. So we can tell temperature from that. Bright lines, black lines. See what it's made of. Some parts brighter than others. Physical conditions, line positions can vary. We can tell speed from that. So we can tell a lot of stuff from a spectrum. And of course, visible light is a tiny, tiny part of the entire electromagnetic spectrum. So we've got stuff that's radiating in radio waves, which are very long wavelengths, all the way up to gamma rays, which are very, very short wavelengths, right? The normal way of measuring this is in nanometers. You'll also see angstrom. A nanometer is about, what, 1/10,000th? How 10,000th? See that on a Friday night. 1/10,000th of a meter, and a angstrom is 1/10 of that. So very, very short wavelengths we're seeing in the visual spectrum. So here's an experiment you can try at home, because I have tried it at home. This is my old observatory, which I tore down because it was falling down. And what I did is I had a telescope and I put a filter on. This is called a star analyzer. It's essentially a diffraction grating in a filter casing. You may remember a year or two ago I wrote an article for the newsletter called The Poor Man's Star Analyzer, and told you how to make one of these of your own with a 25-cent Chinese diffraction grating. My extra ones I brought tonight, so if you do want to build a star analyzer, come see me. So I've got a few. You can order them on AliExpress for 25 cents each or something, but what you can do is you can put them in a filter case and you can get a result that looks like this. This is the spectrum of Arcturus, and you see that you've got the star itself, then you've got the light that's spread out from the star. You've got the 0th order, which is the star, you got the first order spectrum, and then you got second order, third order, and they get dimmer, dimmer, dimmer. The one you're interested in is the first order spectrum. If you analyze that and graph it, it can look something like this, right? It'll have the different colors with different intensities, but it'll always have a peak intensity at a certain wavelength. And if you apply this equation, sorry to have math in the presentation, I know people like that, but there it is. That's the only math in the presentation. If you put that peak wavelength into this formula and solve for T temperature, it will tell you what the temperature is. So in my case, the peak intensity of the spectrum of Arcturus indicated that it was about 4,200 degrees Kelvin, which actually corresponds very closely with the actual figure. So that's a great experiment to do. Spectroscopy is kind of fun, and you can do it with your own telescope without a lot of equipment. Now, if you buy a star analyzer, it's about $200. If you make your own, it's about 50 cents. So the thing about a star analyzer is it makes for brighter spectra because it's a special raised diffraction grating. Any questions so far? Okay, moving along. So we know what it's made of because we see these spectral lines. We can graph them. In the laboratory, we can burn hydrogen and see what lines hydrogen makes. We can burn helium, see what lines, we can cause all of these things to emit light so we can see what they look like. And then we can measure them and see what wavelengths they're emitting on. Now these are angstroms, right? And we can see that we get a hydrogen line at 65, 63 angstroms and a helium line at 67. These are all kind of merged together. So we know this, whatever we're looking at is emitting light based on hydrogen and helium, right? Often a star, right? Because stars are mostly made of hydrogen and helium. So we've actually categorized stars by these physical characteristics. All of these different types of stars have different characteristics. And we have a mnemonic that we use to remember what all these different letters are. Does anybody remember what it is?
Oh, be a fine girl, kiss me.
There you go. Oh, be a fine girl, kiss me. So if you hear that at a lecture on physics, don't call HR, right? Because nobody's being propositioned. We're talking about stellar classifications. So if we look at different spectra for different types of stars, we see markedly different line placement, as well as widths of lines and fuzziness of lines. You'll notice an M-class star has different lines. You don't really see the hydrogen, gamma, delta, and all those kind of lines. You see some other lines which correspond to some other elements. And we know, for example, that M-class stars have a lot of titanium oxide in them. They have been actually preloaded with titanium from supernovas. And so these are stars that have been influenced by their area around them and have collected metals other than hydrogen. Anything better than hydrogen in astronomy is called a metal, right? Ks have calcium, calcium 1, calcium 2, other molecules. Gs also have calcium 2, metals, all the way up to Os, which are OBAs, which are hydrogen and helium. Right? So Arcturus, based on its temperature, is a K-class star. Most M and K-class stars, actually M-class stars are red dwarfs. We don't see a lot of those. We do see some that are supergiants, right? They're cool. They have these spectral characteristics, but they're not actually red dwarfs. Vega is an A-class star. So if you took a spectrum of Vega, look where the peak was. The peak will be in a different place. And, as I said, an M-class star like 61 Hercules has a much different spectrum. So we can tell what things are made of. Easy. So something else that we know is the Doppler effect. Everybody knows what the Doppler effect is. If you see a race car's coming towards you, the sound waves it's emitting are compressed. They get higher volume, and then when it passes you, the sound waves it's emitting are stretched out, right? So it becomes lower. So what you hear is meow, right? Well, light does the same thing. Let me get behind my slides here. Right? So you've got the car, light does the same thing. As you're moving towards you, things are getting compressed. Things are getting higher frequency. What's a higher frequency of light? It's bluer, right? Something's moving away from you. Lower frequency. It's getting spread out. That's red. Something coming toward you very quickly at some percentage of light would look blue. Receding from you would look red, right? So the Doppler effect is really interesting when you start looking at objects. So for example, if a star is moving towards us, we're going to see its spectrum, and we're going to see, say, the hydrogen alpha line, but we're going to see the hydrogen alpha line kind of displaced. If it's moving towards us, right, it'll be displaced towards the blue. If it's moving away, it'll be displaced toward the red. This red shift or blue shift lets us tell how fast something's going, right? It'll give us its radial velocity, the velocity coming away, coming or going, right? What's really cool is one object we can get more information with the Doppler shift. If it's rotating, something that's rotating, one side is coming towards you, one side is receding from you. So what you'll see, based on its rotation, you'll see the line actually spread out. The degree to which that line is spread out reflects the velocity. I remember back in my misspent youth, I ordered a lab from Sky Telescope. This is probably around 1980, where you could look at a spectrum of Saturn and with a ruler measure the shifts, so you could tell what the rotation velocity of Saturn was based on its spectrum. So that tells us how fast we're going. Here's a really cool thing. This was in the newsletter not long ago, but this is a tool called a spectroheliograph. It's basically a tunable spectrometer where if you tune it a little lower than hydrogen alpha, and then tune it a little higher than hydrogen alpha, and take a picture at both sides, and then make the first picture red and the second picture blue, or vice versa, you're going to get a picture like this. Stuff that's blue in this picture is coming towards us. Stuff that's red in this picture is moving away. And this is, you can do this with your telescope if you build a solid, which is a 3D printable spectroheliograph. So, binary stars, same kind of deal. With binary stars, we've got a component that's moving, right? So if we actually plot the spectral lines of a binary star, we will see those lines shift as the star goes around the other star in its orbit. We'll see shifts in the spectral lines that tells us there's something else there, even if we can't see it. Close binaries are so close that it all merges into one star. But we know they're binary stars because we can see their spectrum. But how big are they? Well, this is hard because we want to know the mass of something we can't weigh just by inspection. So this is a series of pictures of a binary star. Two stars rotating around each other. Now they don't rotate right equidistant from each other. They will rotate around a center of mass, which may even be located within the larger object. Like the Earth and the Moon, for example. The Earth and the Moon don't rotate around a point in space. They both rotate around a point that's embedded in the Earth, because the Moon is so much lighter. So it looks something like this. That actually working? Right? So what we see, and this is one way we detect exoplanets, is we see it wobbling, right? We see the star wobbling. Now, if this thing is not like this, where we're looking over top, if we're looking at it from the side, what do we know about it? There's movement. So we can get Doppler readings from it as well, and get the radial velocities that way. So, we go back in time. Johannes Kepler in 1609 figured out 3 laws of planetary motion. He was worried about planets, but it works for everything. First of all, planets travel in elliptical orbits around their center of mass. Right? That's an important one. Planets sweep out equal areas in equal times. Well, that's not as important for our case. But it means when a comet is coming in from way, way out, and it's coming in close to the sun, it's going to go way faster around, whip around, and then it's gone again. Because it has a lot more territory to cover. So it's moving faster because of this law. Third one, the square of the orbital period is proportional to the cube of the distance from the sun. I will be asking you at the end of this meeting to recite that for me as a test. So the square of the orbital period is proportional to the cube of the distance. No, I'm not going to. So remember, we've got the center of mass of 2 objects. We know that if the center of mass is 4/5 of the way over to the larger object, we know the ratio of the masses of these 2 items. Isaac Newton, to the rescue, here he is. He figured out the law of universal gravitation. He figured out the force of gravity is proportional to the mass of the system, of the body or the system. Now, something's going in a circle, so if you put a ball on the end of a rope and you swing it around, what happens? It stands up, right? And what's that force called?
Centrifugal.
Wrong! Centripetal acceleration, otherwise known as centrifugal force. Physicists call it centripetal acceleration because they want to be awkward. Anyway, centrifugal force is the force that a body traveling in a circle is exerting outwards. But what is the force that's balancing that centripetal acceleration? Is the force of gravity, holding things together. So if you can measure how fast something is going in its orbit, like using, I don't know, Kepler's law, you can now figure out what the force of gravity is. You can now figure out what the product of their masses are because you know how far apart they are, because you can see the separation. So, more math than that, but you plug those numbers in, you can calculate the masses based on the ratio. You have now a way to start. Just by looking at it. Pretty cool. So we can see exoplanets. As a matter of fact, I posted a really good presentation that would happen at lunchtime today. I don't know if anybody watched it. It was really good. We're going to try. I think we're going to try to get that person to present to us. So it's excellent. And she takes pictures of exoplanets, actual pictures of exoplanets going around the stars. But of course, most of the time, our telescopes definitely, we can't take pictures of exoplanets. We don't have 10-meter wide telescopes with adaptive optics and coronagraphs to block up the star. All that equipment is limited to the professionals, right? What we can do is we can look at the spectra, and if it's shifted, we know it's moving towards us. If it's blue shifted is moving towards us, red shifted, moving away. We can see in the spectrum of stars whether they've got a large planet going around, just the same way, off or shift. Now, we can also see based on photometry, because when a star passes in front, or a planet passes in front of its star, the light dips a bit. And we can measure that with something called photometry, which you can also do with your own telescope. So, that's a measure of how fast they're moving based on the spectrum, but how far away are they? We used to only be able to figure this out with something called parallax. If you hold your finger up in front of your face, and you close one eye, and then you close the other eye, one eye, the other eye, one eye, it moves, right? So the Earth is in an orbit, which is 93 million miles times 250 million kilometers times 2, right? So you got a lot of distance between those 2 points. If you're looking at fairly near stars, you will see them shift against the background stars. The degree to which they shift, you do a little bit of geometry, and you can tell how far away they are. But unfortunately, that only works with the absolute closest stars that are out there. Another method is we have variable stars, like Gamma Ceti, right? It's a star that gets brighter and dimmer, brighter and dimmer over time. And as a matter of fact, it has a regular cycle, and that regular cycle is actually proportional to its period. A lady named Henrietta Leavitt, who's actually got a really good play against her, or about her, we saw when we were down at a conference one time. Henrietta Leavitt discovered this relationship for Cepheid variable stars, that the period of their oscillation was proportional to their brightness. Based on that, you can tell how actually bright they were, and depending how far away, they'll be dimmer. So if something that's really far away will seem dimmer, and if it's close, it'll seem brighter. But because of this period thing, you can tell what it actually, what the brightness actually was. So now you can say, well, the difference between what it looks like and what it actually is tells me how far away it is. So Cepheid variables, and her boss took credit for it, of course. So Edwin Hubble, who many of you may have heard of, took this to the next step and said, well, here's Andromeda, and I'm detecting Cepheid variables in Andromeda. So this put to bed the idea that the galaxies were in our own galaxy. They were this nebula within our own galaxy. What we discovered is these are actual island universes outside our galaxy, and it was based on these Cepheid variables. So we can use light from Cepheid variables to figure out how far away things are. Not only that, we can also look at the distance they are away from us, and the red shifting and blue shifting, and we can say, oops, I gave myself a couple of minutes. We can look at the colors that we see in the spectrum of these things, and galaxies are either red shifted or blue shifted, and what Hubble discovered is the expansion of the universe is causing this effect. So the farther away a galaxy is from us, the faster it appears to be moving. If you imagine blowing up a balloon and having dots on the outside of it, you blow up the balloon and all the little dots are moving apart, right? So if they're farther away, they appear to be moving faster. If we measure their spectrum, we can see if they're red shifted or blue shifted. And Andromeda, for example, pictured here. Yeah, I took this one like 3-4 weeks ago. Andromeda is actually blue shifted. What does that mean? It's going to hit us. It's coming. 400 million years from now or something, Andromeda is going to impact the Milky Way galaxy. So that's all the stuff you can learn based on the light that's coming to us, which is pretty incredible, I think. So any questions? Yo.
A few years ago, I got a tour of Las Campañas in Chile, and one of the astronomers was showing us this contraption they used for spectra, which was a metal plate with holes put in it,
Oh, yeah, yeah.
and pattern of stars, and then there was a fiber optic cable attached to each one, and then it ran to whatever the heck they used to measure the spectra. But that seemed like a clumsy way to do it, and how does Hubble or James Webb do it without using that template thing?
The reason they do that is they can do like hundreds of stars all at once, right? You could go out and buy a spectrometer that has a fiber optic feed that goes into the back of your telescope. You can point your telescope at an object, it'll feed, your spectrometer. So your spectrometer doesn't have to hang off the back of your telescope, right? That particular spectrometer probably weighs a ton, and it's liquid cooled with liquid nitrogen or whatever, right? So that's why they use fiber optics to get the light there. But the reason they have all these little tiny pattern is they're making measurements of an area of the sky, many hundreds of stars at a time, right? Hubble can do one, right? James Webb can do one, right? Some other ones have wider fields, and they have things like the Star Analyzer, and they can do a whole bunch at a time, but much, much lower resolution. So, yep.
Hey, you may have partly answered this just about end there. The Star Analyzer, is it wide enough field that you can see the zero order and the first order in the same field? Yeah.
Yep. You can actually, there's a modification you can make, which I haven't made yet. You can put a prism, a little round piece of glass that's got a slanted bed, and that can actually push the star out to the side so that the spectra is in the middle, and you get better resolution doing that. So yeah, the Star Analyzer is a really, really cool tool. It's kind of the gateway drug into very expensive spectrometry. We went to Las Cruces, New Mexico 3 or 4 years ago to a spectroscopy workshop. And of course you had the doctor who had his immense observatory out in the, New Mexico to me is like a big gravel pit, right? So he's got on some mountain of dirt out in New Mexico somewhere, he's got this monstrous observatory with a $10,000 spectrometer. But yeah, it's a pretty cool thing to get into. And if you want to get into it, feel free to let me know. I'll give you a diffraction grading. And look for that article. You just have to put it into a filter casing, put it on your telescope, it'll spread the light out, you can see the spectrum of the star. So thank you very much. Have a good meeting. Excellent. Cool.
Can you hear me? All right. So again, thank you to Gord there. One thing that stood out for me was when he had the picture of the sun up there with the blue shift and the red shift. I know optically, if I was looking at it visually, I would have done it opposite. So it's kind of interesting how this changes your whole perspective where you can see it. All right, so we're going to begin our normal meeting time now, and welcome everybody, and those that are online and joining us on Facebook and our YouTube link, welcome. So we just had our beginner session there with Gord Tulloch, and again, I'm welcoming everyone. I'm Dennis Lyons for those just joining us. So we'll be doing announcements shortly. I'll talk a little bit about volunteer opportunities, and later on we'll have Brian Stapp for What's Up. Brian will talk a little bit about the nomination process and where we're at in that. And what's new will be Dr. Michelle Boyce. And then we'll have a short break. And then our main presentation, Roger Venable will be speaking to us. And then afterwards will be, for those that still applying, meet over at Boston Pizza. So basically some announcements, just giving heads up again, there'll be a formal announcement going out later, but the AGM with elections is scheduled for the 13th of January 2023. We're still looking for volunteers for lead presenters. I want to mention about the Loner Scope coordinator is Mike Karakas. And also, we're looking for feedback. We have some more advanced scopes that never get taken out. If somebody's interested in that, let us know. Because otherwise, if no one wants to use these scopes, we may repurpose them for some other use. So we need to find out if the membership has interest in those more advanced scopes. If you want to know what those are, Mike's in the meeting. Can you hold your hand up, Mike? So wander over to Mike and talk to me and tell you a little bit about that. We also have our binocular interest group, Darren Hennig, who's very happy to inform you of what's going on in that. Information on that is on our groups.io site and on the tab for binocular interest group. Also like to promote First Fridays at the Manitoba Museum. Scott, who's taking care of our IT down here, he's the one that coordinates that. If you're interested, he usually posts it both on Facebook and on groups.io to let people know that you can volunteer and let him know that he's coming, just so he knows how many volunteers are coming and what to expect for scopes or binoculars. As I mentioned, Brian Stack is doing collecting nominations and names for council elections as well as appointments. The plan tomorrow is that there will be a members night. I hadn't had a chance to check the weather forecast. What's the likelihood for weather forecast? Anybody look at it for tomorrow? Clouds? Did I hear clouds?
Yeah.
All right. So if we're going to be weathered out, we'll send out a quick blast on groups.io to let everybody know that we're not having it. It's that time of year when we're going to have not bad skies or really yucky skies. Just an update on incorporation. We have formally registered our names. The incorporation papers will go in at the very beginning of January. And just so people know why we're doing it in January, that's when you file your incorporation papers, that becomes your year end for incorporation. And it's just really convenient if we do that because we have our AGM in January. And I'll be very honest, that means that for the councillors or sort of directors that need to sign the documents for the new council, it's all that can happen at that same meeting, and that documentation is taken care of and it's not forgotten. So for those that are interested, if you have any questions about that, contact any of us on council or myself and we'll tell you more about it. But we will be incorporating in January. Calendars for sale, Abdul. Do you have calendars with you, Abdul?
Yes, I do have.
So Abdul has calendars, they're $18 if you're looking for Christmas gifts. Merry Christmas. And of course, Okemic Marsh, once a month, it was last Thursday, I believe. Normally you have it before we're able to announce it before the meeting actually happens. But again, the opportunity is there for members to volunteer and let people know there. All you have to do, so you don't have to pay interest fee, is you bring a scope that you share after the presentation with the public and do the outreach. It's a very nice evening usually. And they're very decent skies, especially looking north of that. So obviously looking south, kind of got a bit of a light going on there. So things we're looking for, these are volunteer opportunities, meeting coordinator, volunteer coordinator. Some of these positions may be filled already. Explore the universe coordinator, webmasters, we're okay for webmasters now. Mentor coordinator, meeting presenters, finance committee, observatory committee, light abatement committee, awards committee, and the nominating committee. Okay, Brian's not here yet. Oh, there you are, Brian. So Brian will be up in just a second. The other thing I would like to pass on is we are working with the Nature Conservancy of Canada at the Tallgrass Prairie Preserve, and we have a meeting this week with National moving forward on probably end up as a dark sky preserve is the terminology they're looking. It's about 26,000 acres that designation's being looked at. So we're still working through that. We're going to want some new readings from us, but it's kind of nice to look at. We are continuing to move forward. Our first dark sky preserve was Spruce Woods Spruce Woods Provincial Park. So we are moving forward with that. There are others that have got interest in other designations. Volcanic Marsh has shown some interest. So there's lots of opportunity for that. For those that would be interested in working with people to educate the public on dark skies and things like that, normally you'll hear referred to in the RASC as light abatement. So if you're interested, let us know and we can get you set up and get that going if you like. Does anybody have any questions? Hey, Brian.
Yeah.
Come on down.
Okay, so I'll talk. Okay, so I'm going to do this first then? Sure. Okay, so he's got it loaded up already, and I'm just going to use this. Okay, so let's talk about what's up for November of 2022. Can everyone hear me okay? All right? Okay, so since we're already halfway through the month, there's not going to be much, but we'll talk about a little bit about the planets, but unfortunately, some of the planets are not really observable. As you can tell, Mercury and Venus are just too close to the sun. Jupiter and Saturn are going to occupy the more of the evening part of the sky, which makes it, I think, relatively easy. Right after sunset, you'll be able to view those two planets, and they're pretty high. Mars is interesting because it's getting closer. It's going to go from 15 to 17 arcs, and it's going to swell up, like I say, 15 to 17. And for the next 2 months, it's going to get bigger. So it's going to get brighter. So this is your chance to maybe have a look at Mars. I'm a big fan of Mars, but unfortunately, I think it was a couple years ago when it was like 24 across, but it doesn't work out like that. Okay, I like this slide right here. So a lot of things are happening right here. We also have Mars. We also have the Orion Nebula, M42, and of course, just up close in Taurus, we have the Pleiades system up there. Now, Mars, like I say, it's back in the retrograde motion. So if you're looking at this side, Mars is going from left to right, but in an upward direction a little bit. But it's very, very slow. So I'm really excited. That was today. Did I miss the? No, I didn't. Did I? The events? I didn't see that. There we go. I don't know if that's something passed a little too quick. Okay, so like I said, much of the month is already gone, but we had the lunar eclipse that happened, but I didn't stay up for it. Was it cloudy? I was too busy with work. It was very cloudy? Yeah, okay. So I think it started around 2 o'clock in the morning. Okay. We do have 2 meteor showers, even though it peaked one on the 12th already, but I'll talk a little bit more about it. We had a lunar meteor shower that's happening on November 18th. Technically, it happened already this morning. But there's a good chance that you'll still be able to see it tonight if you go out. Of course, the new moon is on the 23rd. And of course, Saturn's 4 degrees of the north of the moon. Okay, like I mentioned about this is interesting, but a lot of things are happening for tonight. I already mentioned this. As I mentioned, Saturn and Jupiter are occupying most of the evening. If you notice the time and the date, this is supposed to be tomorrow during the members' night. So this is right after sunset. So you have a really good chance to see Jupiter and Saturn still before it gets way too cold. As I have on this slide here, the Milky Way is not really happening. You have a bit of the core here, but much of the Milky Way is not going to be really visible. But what is interesting about this slide is we still have Hercules, we still have the Pegasus with the Andromeda Galaxy, we still have Saturn and Jupiter. So again, tomorrow's night at the observatory, members' night, we still have a lot of targets to observe shortly after sunset. Now, even though this meteor shower is over, what point I want to make is it's still extended to December the 10th. So which means that we do have another meteor shower coming up. And that's really what I said today, but it's in the pre-dawn of this morning, unfortunately. But we still have a good chance, if it's clear tonight, to see it. Now, since we have these two meteor showers that are overlapping pretty much, so you got a really good chance the next couple of weeks to maybe see some meteor shower action.
I had my camera out last night,
Oh, you did?
a 14 millimeter lens, and I have it taking pictures all night long. I only got two little ones, but before I had my camera set up, there was a great big bright one,
Yeah.
but I couldn't catch it.
Yeah, I caught one. I don't have I should have had that picture I taken back in Arizona. The nice little burner I had there. That was a really nice opportunity. Okay, so that's good you caught something. So it's not happy. Yeah, it's a hit and miss when it comes to these meteor showers, right? It also depends upon where you are in the world and the rotation of the Earth and how it's hitting it against the debris and all this. There's all other factors that's going to affect the meteor shower. And of course the moon. So the good opportunity is, if it's a bright moon, and you're not going to see much. Okay, this is the point I'm going to try to make here. Temperature-wise, I don't know what to say. Okay, as you can see here, I don't know how the laser point. All right, let's try this. All right, okay. So you can see, this is Saturday here. According to this, it's going to dip not too bad for temperature-wise during the meter or during the members' night here. It's going to dip really cold, and Wednesday here, you can see it just drops, right? So you got like minus 20 here. But if you notice here, on next Saturday, it's going to go above 0. That's the forecast. Hopefully it stays true. I'm going to make a mental note of it and see if this is going to hold true. Now, what about cloud coverage? Well, according to this, we are going to get a little bit more snow, but not a whole lot here. As you can see here, it's a little bit of snow coverage here, but for cloud coverage here, we do have tomorrow night. It's not until after 12. Well, sorry, Saturday. So, I guess you ever mentioned about members' night tomorrow night? According to this, yes, it's going to be cloudy. So there's going to be a little bit of break, but not much. But in some nights we do have some breaks here. But next week, next Saturday, as you can see here, it's going to be pretty clear. Now, as I mentioned earlier before, that it's going to be pretty warm. So what I've done here is put side by side, give you a more comparison right here. So you can see the temperature here, it's going to be above 0, and we have some clear skies on the next weekend. So hopefully it stays true. So maybe next weekend we can do some serious observing if we can't do it tomorrow night. All right, so that's what I have for what's up for November 22nd. Thank you. Of course, the GA meeting is coming up in January. So we are taking nominations. I already have a bunch of people lined up for it. But earlier, we had some volunteer work, as Dennis has pointed out. So I'm taking some of these people. What I'm trying to do here is, you got some questions. If you go to the group IO, I put my personal email out there. And if you want to meet by Zoom, I met some of you guys by Zoom, and some of you I met in person. So if you've got any questions about the council, how we operate, how many times we meet, so you have a little bit more background knowledge before you nominate yourself or for someone else, by all means. We do have a lot of positions because we're being incorporated very soon. We're in the process right now. So Dennis and the whole council has been working really hard for the last couple of years. I do mean working really hard. We have a number of committees that are designated to help out this club. And we're trying to make it, work for everyone. And I'm on the nominating committee, the awards committee too, right? So this way we'll never miss any people and have lots of opportunities. I do left my personal email address in the group bio. So if you want to meet with me and we can talk about the positions that we do have open for the volunteer work or for the council or how we operate or how we're going to incorporate it, by all means, send me an email, we'll make an appointment and we'll talk about it. So we still have time. Of course, on the floor, you can always still nominate people. So once the GA starts, you can also nominate some people and or nominate yourself, by all means. If you haven't done this before, and for me, it was a great opportunity to start in the council. Low position, kind of get a feel for how the council works, and see how it works and how you can contribute to the club. The more people who have contribute to the club, the better it is for the club for everyone. And we do have a lot of members here. There are things I think we're going to try to work is events, trying to get more events out there, trying to get volunteers out there with the telescope, like Old Clock Marsh was another good one I'd really like to contribute to. It's a fun time, great opportunity to get some astronomy. All right, so again, if you want to nominate someone, or you want to nominate yourself, you got my personal email at Group.io, just sign in. I made a note, I think Dennis has also said something too, and I think that's Stan, Jay, and myself. So if you want to contact either Stan or Jay Anderson, by all means. And that's it. That's all I really have to say. So hopefully, we'll see you guys there. Thanks.
Great.
Thanks, Brian. Before I forget, at break there's some books up here that have been brought in and donated, so if you're interested in picking them up, come on up. And I'm sure the person who brought them in, as well as there's some Sky News there available. And our next speaker is Dr. Jones.
Testing? Oh, okay. It is working this time. I'm not good at these things, so. Okay, so I've just selected a couple of topics for what's new. I wish we could type before topics. December 24th, 2021, the Mars InSight lander, which is used to study seismic activities on Mars, detected a magnitude 4 Mars quake, which was later attributed to an actual meteoroid impact on Mars, which was actually imaged by the Mars Reconnaissance Orbiter. Also, more recently, in September, another one was found that was attributed to an impact. Now, the thing about this particular one, December 21st, is that this was the first surface wave ever detected on Mars or on another planet. Normally they get just stuff from more interior. And basically, as we know, we monitor earthquakes on Earth. We can actually tell something about the structure of our planet into that. And so that's the idea of the Mars InSight lander. And it can basically look at various strata and layers down to 4.8 down to 30 kilometers. Oh yeah, this is a sound of that impact. Let's get it to play. Here's the volume. Does anyone hear that?
No.
It will build, but I don't know how to control the volume. The sound might not even be on. Well, you can see it. So you can use your imagination. It actually sounds very similar to the wind on Mars. If you listen to those recordings. They have to always downstep these frequencies for our ears, so if it's high or low frequency. So this is an image from the Mars Reconnaissance Orbiter. Basically, the impactor was estimated to be 5 to 12 meters across. If that were to impact Earth, it would have just vaporized because our atmosphere is extremely thick compared to Mars. And it created an impact crater roughly 150 meters across, and the ejecta went as far as 37 kilometers. So that's the crater that was imaged. NASA now has up a 3D rendering of it, a movie that you can also see. Okay, so the next one is if you remember the Event Horizon Telescope, it was a big event when we showed, I think it was M81, maybe someone can correct me, was the first black hole that we imaged. And at that time, they were also imaging the one at the center of our galaxy, Sagittarius A star. But that was more complicated because it has no jets or anything coming out, fortunately for us. So that took much longer to image, and that was released in the spring of 2022. This is an animated model of the rotation of the black hole at the center of our galaxy, and it kind of models the rotation frequency that's actually seen in the images. So this is what it might look like closer up. Just a quick reminder of general relativity. Basically, massive objects tend to deform space-time. So this is the classic rubber sheet model where you can imagine a rubber sheet and then you place a large mass on it and it deforms the sheet. And so if you then take a marble and push it on that sheet, it will actually make a small indent and can be put into an orbit or a comet trajectory and so forth. There is a nice YouTube video here where a guy actually has made one of these, and you can put the moon going around a planet. You can create a little solar system, and he does all that. And of course, it's a model, but you have to think of that in 3 dimensions, and then add some space-time gobbledygook. Okay, so black holes, basically, they're so massive that light cannot escape. And so you could actually work that out. You have escape velocity from Earth. You sort of have a sense of that. Well, you set that escape velocity to the speed of light. The object is so massive it can't escape. And you get this equation, but let's forget that. It's just 10 to the minus 25, which is what times the mass of the object you're interested in to find the radius that you have to compress it to. So 10 to the minus 25, if you prefer, that's your mass divided by 1 with 25 zeros after it. Okay? So our sun, we'd have to compress our sun to 2.9 kilometers in order to form an event horizon. And at the event horizon, if I'm standing on the event horizon, if I could without being spaghettified, and I looked along the horizon, I would see my back, because my leg is just forming a circle. I would see the back of my head. Earth, if we squash Earth down to that point, it would be about 9 millimeters in radius. And if you squash one of us, it'd be much, 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 much smaller than a proton. So it's very, very tiny. In fact, we probably have that, but that's another story. So this is the black hole at the center of our Milky Way. And I got this from Knowledge magazine, and I added this mass here. It's basically, we have a 42, basically we take 42 million of our suns and compactify it down, we get the black hole that's at the center of our Milky Way. So it's a 42 million solar mass object. And so you kind of have the dimensions here. The gravitational diameter is about 12 million kilometers across. And then all this stuff here, what's going on is it's sucking in matter and it's accreting and getting very hot as it tries to spiral into the black hole. And we're seeing this in the infrared. And actually, sorry, in radio wavelengths, because we really can't see to the core of our galaxy. There's just too much dust and stuff. So you have to use radio telescopes. So what you're seeing is the accreting, the heat, basically, from the accreting matter and the radio range. And so that's all that material around this black hole. And so they didn't actually build the black hole because all the light disappears. You're just building a silhouette of the black hole with all the matter going around it. And so this, they're calling it a shadow, which is about 60 million kilometers across. The Event Horizon Telescope basically uses a bunch of radio telescopes on Earth, and they're all synchronized together to basically build interferometer or telescope that's the size of our planet. And the way that works is if I take two telescopes and I look at an object, I can scan across the object and look where the light interferes constructively, adds up, or cancels. And so I can scan across and get that image. It sounds pretty straightforward, but this probably took them years to do the analysis. Plus, it was several independent teams that would do it because there's sort of a bias or psychology in astronomy in terms of, well, is that object this or is that object that, because you can't get to it physically. So they do that to remove any bias. This is just this image here, the black hole is tilted at about 45 degrees facing this. Even though, if it was like if we just saw its edge, you could still see an image similar to this, because the gravitational field is so strong that the light waves get bent around it. So if you imagine looking at a disk like this, or even say Saturn like this, Saturn's so massive, you would see the backside of Saturn, because the black hole is just so massive. Okay, so you end up seeing this whole disk as a result, even though it's at an angle. So the last subject I wanted to talk about was light echoes. I thought this was interesting. This is from a website called Astrobytes, and basically there's like graduate students who read papers and then make them water them down so they're easier to digest. And this one is called light echoes. So basically, what I'm showing here is supernova 2016. And so we get this supernova event, which is in Centaurus A galaxy, which is 65,000 light years away. And basically a light year is the distance traveled by light in 1 year, and light travels at 300,000 kilometers a second. And it takes like 8 minutes to get to the sun at that speed, just to give you a sense. So this takes 65,000 years for light to get to us. Intervening that, however, is this dust cloud. So there's lots of dust in interstellar space, and that's of course where star nurseries are and so forth. This dust cloud is about 190 light years thick, and it's about 620 light years away from this event. Okay, and so we look at this, and what we end up seeing is these rings. Okay, so here are the images of that. So this was taken between 2016 and 2021, 8 epochs, so eight times over that period. The first one was taken 75 days after the event. You can see here's the day 7, 7 days, and then so forth. So you can see these rings forming as this is taking place. And these were taken in 3 different color bands using the Hubble Space Telescope. And then below here is at the bottom is a color composite image. My mouse seems to have vanished. But at the bottom, yeah, these are color composite image of that event. That's what they call light echoes. Okay, so that's it for the selected topics for what's new this month. Any questions? Nope? Okay. All right.
Thank you very much.
All right, so we're just slightly ahead on our agenda, but we're still going to take about a 10-minute break. Our speaker is going to be able to start a little early. So we'll break until about 1/4 after, and then we'll come back. Thank you very much. And welcome to all those again that are online. Declination, opposition date, parent size and season, recent images and drawings including the dust storms, and some recommendations for observing Mars, and the operation of Mars by the moon on Mars' date of opposition. Please welcome Dr. Roger Venable.
Share my screen. Let's see that one. Let's see. Get this out of the way here, change the view. Okay. Well, thank you for inviting me to talk. Do you hear me okay?
Yes.
All righty. And I want to have a shout out to Mike Caracas, who I understand is with us. He's been sending me some really nice images of Mars this year. This graph shows the elongation of Mars from the sun as the solid line. Do you see my mouse in front of the graph?
Yep.
Okay, good. The elongation coordinate is on the left over here. It peaks at 180 degrees, of course. And the elongation goes up to just short of 180 degrees on December 8th, which is coming up here in a few weeks. The right-hand coordinate is the declination of Mars in the sky of Earthlings. And as we look at Mars, it's going to have a declination in our sky greater than positive 20 degrees, starting on roughly September 1st and lasting through early June. This is the farthest north and the longest it's stayed that far north since the 2009-2010 apparition. This northern position in our sky is rendering Mars easier for Canadians to observe than it has been since 2010. The last time Mars was so well positioned for observers in the Great White North was in 2010. This graph shows the angular diameter of Mars, which will peak at about 72 seconds of arc. The angular diameter in arc seconds is on the left coordinate, and it is the solid line here. And it will be 17.2 arc seconds at the closest approach, which is on the 1st of December, not the date of opposition. It's not the date of opposition because Mars is on the outward swing of its elliptical orbit, and so it's closest to us just a few days before opposition. The magnitude of Mars, the brightness, is on the right-hand coordinate of this graph, and it's the dotted line in the graph. You notice some squiggly effect here. That's a complexity which I don't think I have time to explain, but it's real. And Mars will peak at a magnitude of minus 1.96 around early December. And that's brighter than Sirius, but less bright than Jupiter. As you know, Earth orbits the Sun in about 365 days. Mars takes 687 Earth days to orbit the Sun. So, when a year goes by on Earth, and Earth has returned to the same place in its orbit that it occupied a year before, Mars has gone only a bit more than halfway around its orbit. Therefore, no opposition of Mars can occur in the year after opposition. The opposition cycle of Mars is about 2 years, 50 days. The previous speaker dealt with this. We'll go on. Now, the images of Mars that I'll be showing are rotated 180 degrees. That is, north is at the bottom, south is on top, east is on the left. East is defined as the direction toward which a planet rotates. So Mars, in these images, will be rotating toward the right, and toward the left, and west will be on the right. And this may seem strange to people who are not familiar with the alpha way of presenting the planet Mars. So, what should we be looking for on Mars? First, you want to look for albedo features, which are bright and dark areas on the surface of the planet. Mars and Mercury are the only two planets on which we can see the surface features, and the bright and dark areas on Mars are striking. This is a good image of Mars. The dark areas appear gray in this image, but visually I have always found them to appear blue or green. The blue or green visual appearance is thought to be a contrast effect due to the bright orange features adjacent to them. The color of the bright areas is often described as ochre, perhaps because no one really knows what ochre is, so they don't object to it. Here is another good image of Mars showing the bright and dark areas at a different longitude of that planet. Note that there are mainly two categories of features, bright ones that appear reddish or orange, and dark ones that are gray in this image, but as I said, often appear blue or green to a visual observer. There are intermediate shades of brightness, as you can see, but the overall appearance is dominated by the two main color and brightness types, orange and bright, and gray and dark. Here is a sequence of images at another longitude of the planet. This sequence was made over a period of 3 hours. At these longitudes, there are fewer and smaller dark features, and this causes the planet to appear brighter in the sky than it does at other longitudes facing Earth. And it's that rotation of Mars showing occasionally this bright side of Mars that causes the funny squiggly lines in the brightness graph that I showed you. Here is still another longitude. The very bright area at the center of the left, right over here, is Elysium, and it is always bright. The dark feature near the center on the right over here is called Syrtis Major, and it is the first feature ever identified on Mars, first seen by Christian Huygens in 1659. We need to look for clouds on Mars. I'm going to go back 4 slides. There are clouds in this image. Firstly, you may notice the bright North Polar cap. And this, although it appears that we're looking at the cap, this is also covered by clouds, and it's brighter along its edge because there is an intense jet stream along the edge, the North Polar front, and it has dense clouds. Over here on the left, you see sort of a faint brightening over here with a slightly bluish tinge. This is called the Syrtis Blue Cloud. This is the Syrtis Major over here, and that's the Syrtis Blue Cloud. I'm not sure why it looks blue, but when Syrtis is near the limb of the planet, a cloud over it often makes it look blue. Over here at the sunrise limb, we see this sunrise haze, and these are often present at sunrise on Mars. They form during the night, and they don't rotate across the Mars as Mars rotates because they sublimate and disappear due to warming as Mars rotates, so that they're always just visible on the sunrise edge of the planet. This image is essentially without clouds, except that the clouds are on the edge of the North Polar cap and over the cap. And clouds over the cap are called the North Polar hood. And in this image, we see the same features, the dense clouds at the edge of the North Polar cap, and that's the North Polar front. And we see the sunrise clouds, as I mentioned before, but we're also seeing these topographic clouds. Most of these are what we call orographic, that is mountain related. And this one is, this one is probably at Olympus Mons, and that one's probably at Arceum Mons. This one is probably at Notus Gordiae, which is a high ridge on the Amazonas area there. And let's see, this image will at first appear as though there are no clouds in it. However, actually there are clouds that are just very hard to see. By the way, this is Elysium, that bright area that I mentioned. It's not due to clouds. But if you look at the blue image, you notice that in blue, you can barely see the albedo features. That is, the bright and dark areas of the surface. But blue makes the clouds very bright, so you can see a haze here over the sunrise that's actually very subtle, but that's a cloud in this image. There's a little brightness right here, but that's not a cloud. That's just some penetration of the brightness of the lesion. Okay. Now these are some interesting clouds. There are 3 clouds arranged from east to west, left to right, the left side of the center of the image, right up here. And you notice they're not much visible in red. Red penetrates through the clouds. They're a little bit visible in green, but blue really shows them well. Red shows the albedo features, blue shows the clouds. The cloud on the left is over Noctis labyrinthus, which is at the west end of the largest canyon in the solar system called Valles Marineris. Noctis labyrinthus is frequently a site of cloud formation, and the reason for this is not clear to me. The middle one of the 3 clouds is on the eastern slope of RASC Winnipeg, a huge volcano, while the cloud to its right is a downwind cloud created by the mountain. RASC Winnipeg is a very frequent site of clouds, some of which are peculiar. Polar caps and hoods. Now, the visibility of the polar caps always depends upon the orientations of the axis of Mars to the position of Earth in their respective orbits. This slide is of simulated images made by a computer program that Jeff Beach has. Back in May, we were looking at the South Polar Cap, and dedicated observers monitored the sublimation of the seasonal South Polar Cap as it grew smaller, and then it tipped away from us and became essentially invisible, and when it did that, we saw the clouds over the North Polar Cap, the North Polar Hood, and they're prominent right now, and shortly we'll be able to glimpse the South Polar Cap again, just because of the changing orientations of the 2 planets. And the polar cap is going to be tiny when it comes into view again, and it'll be pretty hard to visualize. Then late in the apparition, we'll have a good view of the North Polar Hood again, North Polar Cap, though Mars will be considerably smaller. Here are 3 drawings of Mars made on the same night by Paul Abel using a 10-inch Newtonian reflector. Notice how he has meticulously documented the visibility of many albedo features. He emphasized the unusual appearance of the North Polar Hood here, and he emphasized it by enlarging it here, as it was asymmetrical, the dark area north of its southernmost extent. This view shows complexities in the North Polar Hood. The right areas are denser clouds. You can see them best in blue. There is one big one, and you may see a few small ones. Let's see. I want to make sure I'm discussing the right image here. Okay. The blue light image shows mainly clouds, and you're really lucky if you can see the polar cap at all. In the red image, you can actually visualize the polar cap right here because you're seeing through the clouds of the North Polar Hood. Red penetrates through the clouds. Blue shows mostly clouds and doesn't penetrate through the atmosphere. But the edge of the polar cap is right along the tip of my pointer, right along there. And this is a row of clouds above it. And this is a cyclonic storm. And when it's north of the polar front, we call it a polar cyclone. That's a polar cyclone. This is a polar cyclone, all different colored views of the polar cyclone on Mars. This shows a good view of the North Polar Cap. the polar cap is this perfectly horizontal line right there. That's the edge of the polar cap. In this view, the North Polar hood and its associated outward band, the polar front, is displaced from the North Pole. And that very commonly happens. It displaces upward like that. Usually, when it does so, it's associated with storms in it. And when you see weird C-shaped structures like this, that's usually a storm. Oh, this is the image that I wanted to show you. There are several lumps here in the North Polar front, and these are cyclonic storms in the North Polar front. So let's talk about frontal storms. Now this is from the Encyclopedia Britannica. In the left picture, the surface winds are depicted, trade winds above and below the equator, with the intertropical convergence zone between them and westerly winds in the temperate latitudes. Notice the polar high, with its winds blowing in a direction opposite that of the temperate latitude winds. In the right picture, the upper elevation wind currents are shown. Storms occur whenever two cells with oppositely directed prevailing winds flows meet. Jet streams are the magnification of the wind effects at these boundaries. So we have jet streams along the polar front, where the polar high winds and the westerly winds are traveling in opposite directions. We also have jet streams in the tropical area down here, and that's because they're traveling in opposite directions. But, so those are big sources of storms. In the intertropical convergence zone, we also have heavy storms. Now on Mars, turns out that the Ferrel cell is very weak, not present most of the time, kind of intermittently present. The Hadley cells are strong, and the polar cells are strong. And because if you think about the direction of the winds, when there's no Ferrel cell, it's a mess between the Hadley cell and the polar high. A lot of turbulence there, and that's where most of our dust storms begin. But understanding these cells and wind patterns, I want to mention one more thing. This intertropical convergence zone moves north and south with the season on Mars, which it doesn't do on Earth. In northern summer, when it's hot, when it's hot, this is Earth, so the north is up here. In this summer on Mars, northern summer, the intertropical convergence zone moves up to 30 degrees, as much as 30 degrees southward, so the Hadley cell crosses the equator all the way up to the polar high. And the Hadley cell on the winter side is in much smaller extent. Now this is also from the Encyclopedia Britannica. It shows the evolution of the jet stream with the break-off of cold air masses from the North Polar region of Earth. In A, the upper left, the air current rotates rapidly around the polar region. It is somewhat unstable in that the forces that constrain it to its path are weak. In B, the instability is manifested by an undulating jet stream. Many storms that occur in the northern temperate regions are due to this undulation without a cold air mass separate from the polar high. In C, the undulation is more pronounced, and a cold air mass is moving southward and causing storms down in the areas where people live. And indeed, the cold air mass has actually broken off and is going to travel southward and cause storms, in this case, across the continent of Asia. It'll be limited to some extent by the Himalayas in there, and it'll travel through China. And meanwhile, when that happens, the polar high regains some of its stability, and the jet stream gets sort of back to the original position, because a lot of the vortex energy, vorticial energy, has been transferred to the air mass that broke off. This is a spacecraft view of a type of storm called a nor'easter. If you look at the land surfaces in the picture over on the left, you may recognize some of them. This is the island of Cuba. This is the peninsula of Florida. This was the eastern coast of the United States. I see Chesapeake Bay right here. A little bit of Long Island, New York, right in there. This is Lake Ontario. This is partially frozen Lake Erie. Lake Huron is partially frozen. The Georgia Bay looks completely frozen. Of course, the James Bay and the Hudson Bay up here are frozen. I think Winnipeg's right about here. Do you think that's where it is? Somewhere over there. This storm is called a nor'easter because the winds are rotating in a counterclockwise direction. So that the maritime provinces and the northeastern U.S., as well as the fishing banks and part of the Atlantic Ocean, get strong winds from the northeast, often along with heavy rain. Although this can occur due to an extratropical hurricane, such as Hurricane Sandy, it most often happens with a cold air mass from the northwest. It moves down across Quebec and arrives down in the ocean up here. This slide is exactly the same as the previous slide, except I've rotated it 180 degrees, just as I do with Mars images. In other words, this shows south at the top and north at the bottom. And if you'll bear with me, you'll understand why I'm doing this. In the next slide, I just blur this image. This is a Gaussian blur, and the 1 sigma radius of the blur is 1/4 of the distance across the image. And it makes you see this storm with essentially the same resolution that amateur imagers see storms on Mars with. And you notice there's a very dense part of the storm here and two long, might call them pincers, that stick out this way, and that's characteristic of some of these storms. Not all of them have just that appearance. But I want you to keep this shape in mind. Keep this shape in mind for a storm. And then, look here, right here on Mars. And there you see it. That's a nor'easter, okay? That's a storm on Mars. Now this is a Hubble Space Telescope image from 1977. This one is just outside the North Polar region. And this is an extrapolar storm that arose in the polar jet stream of Mars, much like a nor'easter in the Atlantic. This slide shows two views of the North Polar region here without any storms. It's quiescent. It's sometimes like this, and I don't want you to think that it's always stormy. This shows the first North Polar cyclone detected by amateur observers in 2008. The observer did not know that he had detected it. I told him about it. It's a bit hard to see. Can you see the little whitish circle right there in the North Polar hood? It may be easier to see in the enhanced view right here. But that circular feature is a circular storm. That's a cyclone. These images were made on the same night by the same observer, about an hour apart. They show a white spot down here in the North Polar area. All three images do. When you look at this diffraction effect at the limb of the planet, this is due to diffraction in the telescope, this bright, they call it the rind here. You may want to attribute this spot to just diffraction from the white polar hood. But as he imaged later, it had moved. It's now this big. And as he imaged later, it had moved up here. You see, it's really up in the North Polar hood. And that shows that it's not an imaging artifact due to diffraction, because it's rotating with the planet. By the way, this is Olympus Mons, and it likewise is rotating with the planet. This one, I'm thinking, is something like that. It's a little hard to. This is Arceus Mons, Pavonis Mons, and Ascraeus Mons over there. And they're so near the terminator that it's a little hard to see, but I think that would be Arceus, Ascraeus, and Pavonis. So we've seen the mountains. Two images were made by the same observer on two successive nights. Feature one is in Elysium, that right area, and it's bright because there's frost on the 41,000 foot high Elysium Mons. That's 41,000 feet above the mean surface level on Mars. Feature 2 is Meat Crater. It's a little hard to see in this image, but there it is, and over here it's brighter. Feature 3 is, by the way, has frost in Meat Crater. That's why you can see it. And they don't move from night to night. They're fixed with the planet features. But this white spot right there, here is to the lower right of Meat Crater, and here it's almost right below Meat Crater. It's moving from day to day. So you know that that's a storm in the North Polar Hood moving eastward during this one-day interval. But you can see from these last couple of pictures how important it is, if you're interested in the weather on Mars, to take serial images, often just an hour apart, to watch things move with the rotation of the planet, and sometimes a day apart to see if they're moving from day to day as storms do. Here, there is an intense storm along the polar jet stream. You see it right there. The clouds are really dense in blue light, but you can't see the storm. In green light, you can see it. And in red light, you just see the northernmost lip of it, because the clouds are thinner here. And I don't see anything peculiar. This is really a very typical North Polar Front storm. This is a very intense one. Again, you see that clip-like shape that we saw with the nor'easter. And this one is still in the North Polar Hood. It hasn't migrated at all. But you can imagine if you did night-by-night views of this. Here we have two views about 50 minutes apart or something, 45 minutes. But if you imaged it night-by-night, you could elucidate the behavior of this cyclone. All right, now I'm going to show you something you may not be aware of. First, let's look at the blue image. You see the North Polar Hood is very dense. It's large. It extends over significant longitude here, latitude of the northern part of the planet. If you look at the green image, which penetrates through much of the clouds, you can get a better idea of where the really dense clouds are. Here we have a polar cyclone, and here we have another cyclone right next to it. You see the S shape there? Two cyclones. And here we have another polar front. The polar cap is here. That's the edge of the polar cap. It shows up in red as well. That's the edge of the polar cap, and what's north of that is polar cap. The reason it's not brighter is that it's under the clouds, and so it's not well illuminated. The clouds are high in the atmosphere, and comparatively, and of course, they're very brightly illuminated by the sun. Now, the key to understand why I'm showing you this is to see that this semicircular storm does not form a full circle in green light, but in red light it does. You see it in red light here as a circular storm. Now the red light barely shows any clouds, so why would it show a southernmost part of this arc up here better than green light, which shows clouds better? The reason is that this is not in the clouds. This has to be on the ground. Otherwise, if it were in the clouds, it would show up well right here. In fact, it's brighter than the lower part, because the lower part is partly masked by clouds. So we've got a feature on the ground here, and it's circular, just as the cyclone is circular. Now, I want to give you a quiz. If you there are three things that can cause brightness and red light on the surface of Mars. One of them is dust. Well, I assure you this is not a dust storm. We can go on, we'll talk about them later. Another one is frost. Frost. And another one is snow. Now, we do know that the snow's on Mars. It's been documented by several spacecraft plus the Mars Polar Link. So, let me ask you, if you wake up and find frost on the ground, is the sky going to be clear or cloudy? Unmute and tell me. I need to hear the answer.
Clear.
Clear, right? When there's frost, the night is clear. Now, if you wake up and find snow on the ground, or snowing, is the sky cloudy or clear? It's probably what? Cloudy, right? Okay, look at the clouds now. This is cloudy. we're seeing through them. So what we're seeing on the ground is not frost, it's snow. This is snow on Mars. I hope you believe me. Okay. This is another example of the same thing. These are images by Damien Peach. The storm visible at the edge of the North Polar Front is right out here. That's the densest part in blue light. In green light, we can begin to see, as with the previous image, we see a little bit of a circular feature in green light. And in red light, suddenly we can discern the polar cap. We can see that's polar cap. The clouds are barely visible, all the clouds before, and yet we have this relatively intense feature, which is not intense as a cloud because it's not as intense as the rest of the clouds in the other images. It's more intense in the clouds here. That's telling me that it's on the ground. This little round thing is what I'm talking about. It's a circular feature accompanying a circular cyclone, and it's on the ground. And the weather's cloudy, so it's snow. Now this one lasted about 3 or 4 days before it finally disappeared. Here we have multiple fronts. Again, we see the North Polar cap right here. We can see the edge of the North Polar cap. We have a front here, North Polar front. Here we have another front, and it has 3 storms in it. And up here, we have a further extension of clouds from the north area extending further south. On this side, we have another front coming up this way, and it looks to me as though there's another cyclone over here. So this is really common. We see this kind of thing often in the North Polar Hood. Let's look for dust storms. Now this is a series of 6 images made on 8 nights. There are 2 nights where he had to drop out because his sky was cloudy. Made by Clyde Foster in 2020. I want to draw your attention first to this nubbin right where my pointer is. You're still seeing my mouse pointer, right? Yeah. Okay. Well, there's a nubbin in the North Polar Hood. It's not a smooth North Polar front, so we know there are storms in it. And that nubbin persists the next day, and it persists this day. Now actually, as I look at this, I think that it actually looks a little bit pink compared to its appearance over here, which is a blue-white. That's sort of almost a pink-white. It might be starting to entrain dust already. Here, there may be a little bit of pink in it also, but notice it's pointing down. It's moving northward. And in here, the same storm has moved northward, and what happens when it moves northward is it warms up a bit. And that, because the sun is shining, it's out from the clouds, and that wind entrains dust, and we have a local dust storm right here, and it doesn't have clouds over it because the clouds have sublimated due to the sunlight. And the next day, we still see it over here, although it seems to have enlarged, and it's not so dense. So that suggests that it's likely to dissipate over the next few days, which is just what it did. And so that is a dust storm that arose from the edge of the South Polar Hood, and that dust storms arising from the South Polar Hood are very common. We see them in the North Polar Hood. We see them every year. Now, scientists, Mars scientists, who have counted dust storms, small dust storms on Mars, believe it or not, say that about 1,000 occur throughout the Martian year, that is in the 687 days, about 1,000 small dust storms, almost all of them very small, even smaller than this, and they only can see them with spacecraft orbiting the planet, and most of them just dissipate in a day. Now that sounds incredible, but we amateurs with our instruments are, I would guess, 4 to 6 or so per apparition. An apparition lasts about half of the Martian year, you know. And so when we pick up a few, when you realize there are hundreds times more than what we see, it's kind of daunting. Okay. Now, this is a dust storm on the right. And the key to this image is this regional dust storm on the right. This is taken September 23rd at 1927 UT. And this is an image from a previous apparition from about, let's see, 2007, so we're talking 15 years ago, by David Tyler. And the reason I'm using it is because it has almost the same central meridian and shows good albedo features. This central meridian is 60 degrees west, and this one is 63 degrees west. And I have cropped it here, masked it so that you can more readily relate this image to this one. There are many things that are on this image that are obscured over here. And what you do when you compare them, you say, is that? Wait a minute, I'm not sure. How come that's dark and this is bright? You know, you start thinking like this. Now here's a curve with a dot in the center and a curve with a dot in the center. So we can see Solus Locus. That's called Solus Locus. But all this stuff, Margariferi sinus, Aurori sinus, Chrysae and Xanthe, and look at this great big area. This is Nelaicus, Locus, and Mariacidalium. They're gone. They're just gone. They're covered by dust. We do see two spots here that I think I can discern here, but you know, there's a spot up there that I barely can see, if I can see it at all. The point is that dust obscures the normal albedo features. So if you have a big dust storm, like a regional dust storm, often you can't see much under it. The other thing is that the things you do see here are false albedo features. I mean, you'd be hard-pressed to get this little dark arc right here and find it over here. I probably wouldn't believe it if you said you did. But anyway, here it's really dark, and it's not here. So, you know, you see false albedo features because the way the dust is scattered in intermittent large clumps dims some albedo features so that they're just not readily recognizable, and it makes the adjacent features look darker and so on. All right, now this is taken the very next day, the 24th of September, and I again have a comparison view. This one's made in 2009, and again I've cropped it here to make it match this so you can better compare the orientations of the two. This is a mistake. This central meridian is 30. I'll have to correct that. This is 32. So they're very similar meridians. And you can see that most of this whole area is just not really discernible over here. You do see the North Polar hood and the dark area, poorly illuminated polar cap, but even that's not well discerned. You just see that, look at all these areas, they're just not there. And so this was a fairly dense regional dust storm that lasted about a week or two, and gradually there was haziness left throughout the Martian sky afterwards for about a month. But this was quite a dramatic dust storm we had in September. All right, and now the last thing I'd like to point out is that the albedo features on Mars are slowly changing over the years. This slide shows 5 different drawings of the Syrtis Major region. I don't want to spend a lot of time on it, but I want you to notice that the shape and proportions of the Syrtis Major have changed a lot, and perhaps there is a cyclical pattern. Notice this Syrtis Major appeared pointed at its northern tip in 1877, and again in 1954, and Toniati drew it as almost bulbous here at the bottom, and with a prominent wide curved feature. The curved feature is barely visible, if at all, lately, in later years, and the bulbous bottom seems to have resolved, and so on. So these things appear to be changing over the years. Mars is small, and therefore difficult to observe. It requires high magnification. The smallest telescopes used by Albert Introduced Mars monitoring are of about 100 millimeters aperture. A telescope of 200 meters aperture or larger is recommended. Optical collimation must be meticulously maintained. We're talking about getting the best resolution from your telescope. Your surroundings should be thermally neutral to avoid air currents that disturb the view. You don't want to look over somebody's house. You don't want to set up on a driveway that's in the sun all day long. It's good to leave your telescope in this thermally neutral environment for an hour before you start to observe, because you want the telescope to have the same temperature as the ambient air, again, to avoid the air currents that disturb the view. Take time to focus. In my experience with observing with other observers, I find that most of them do a snap focus in about 3 seconds. And I'll tell you that if you're observing the planets, pointing your telescope at a planet is difficult, makes focus difficult. Planets are hard to focus on. The scintillation on the planet disturbs the view, and you can't get it really sharp. I recommend you focus on a nearby star, and the brightness of the star depends on your instrument. If you have a go-to mounting, you can go to the star at high magnification, focus with great care, take 10 minutes to focus. You will not ever regret it. And you do that after all the thermally neutral things are accomplished with your telescope. Then you do the focus. And when you can see diffraction features, that is, you can see the diffraction spikes made by your secondary mirror hole, and you can see the diffraction rings around the star, and you are sure that you've got the clearest view of the diffraction rings, then you're in good focus and you're ready to observe the planet. Now, different color filters can require different focal points when using refractive optics, so be aware of that. If you use red, green, and blue filters, as people do on Mars, and you're using a refractive optic, it's going to be frustrating because you have to refocus after the filter. Look for a long time. The longer you look, the more you will discern. You'd be amazed at how this works. You think, well, I've been looking at Mars for 30 seconds now, I guess I'm done. You look for 30 minutes, and you will be amazed at how many things that you discover as you continue to look. And then the other thing is, you want to use color filters, because red will really emphasize albedo features and dust clouds, which are brighter than the background red of the bright areas of Mars, and deep blue for water ice clouds. But remember that albedo features will scarcely be visible in blue light. Now, if you're not familiar with the features of Mars, just use a map or one of those globes that Sky and Telescope sells, or some other type of guide that will tell you what you're looking at. The other thing I would say is join the Association of Lunar and Planetary Observers. It's cheap. There's its website. You just click on the membership tab among the headings on the home page, and they'll direct you about how to join. Done. Does anyone have any questions? Is everyone asleep?
So when you talk about these northeasterners, these big storms, what do they equate to? The ones on Mars, how do they equate to storms on Earth? How severe are these storms?
Could you repeat the question, please?
What do you want to pass it along? Say it again. I don't know. No, what was your question? When there's a storm, like that northeasterner equivalent on Mars, how severe is it? What would it be like if it was on Earth? How severe are these storms? How much, dust gets thrown up? How bad are the winds?
Yeah. Well, I don't have that information. The wind speeds are measurable by some of the spacecraft, such as the MAVEN spacecraft, which is specifically studying details of Martian climate and things like that. And I just don't have that information for you. Fortunately, none of our rovers entered any severe storms. Some have been struck by some of these willies, as they call them in Australia, minor little tornado-like things, but from the standpoint of severe storms, none of them have been struck by them.
Hi, Roger. Mike Ryan here. Thank you very much for your presentation. Can you hear me okay, Roger?
Let me say that from questions in the audience,
question.
Mike's going to ask a question. Hi, Roger. It's Mike Raffis here. Sorry, we're having a mask mandate here at the university, so we're covering up. Thank you very much for your presentation, Roger. Really appreciate it. Question: when you're looking at a lot of the images that you're showing, there are a lot of RGBs, red, green, blues, and you're discerning a lot of information about the cloud patterns and the dust storms based on that color palette. Is it advantageous? I was wondering, you didn't get into the infrared spectrum regarding that, and is it worthwhile for amateur contributions to look at imaging in the RGB as opposed to maybe infrared? Can you elaborate on that a little bit?
Only a little. Firstly, I usually don't like to talk too much about specifics about instrumentation and observing and image quality. And the reason is that most people who are good at things are self-taught. And if I try to teach them, then I will expose myself to a lot of criticism. And that's not what I do. I look at images and I diagnose what's going on Mars. In other words, my role is different. Where a lot of discussion about imaging techniques are done, and I think those are good places to make those discussions. We usually, on the Mars Observers group online, Group SIO, we just try to talk about Mars, not so much about imaging. A little talk about imaging, but not much. I really try to keep that to a minimum because you just get into a lot of arguments about it. And here's one of the concerns I have. I can say two things. Firstly, when you use red, green, and blue filters, you know exactly what wavelengths you're imaging in, and you know whether those filters overlap and various other things. And furthermore, you have the full light of the camera exposed in that color. When you use Bayer color, you're not even getting the full light in each color. I think the signal-to-noise ratio is going to be less when you use Bayer color. Secondly, using red, green, and blue filters introduces a time difference in your image between the red, and the green, and the blue. Refractive optics, if you're refocusing, and blue filters actually cause a significant time delay if you have to refocus. And this is now obviated by Win2 post processing, in which you do what they call a deep rotation, and so the time difference doesn't seem to make much difference anymore. And I think this has been a boon for imagers who prefer to use red, green, and blue. Also, one of the problems with Bayer imaging, color imaging, is that you really just don't know the wavelengths you separate. And I think that in my experience, the color-separated Bayer images do not reliably, with all different cameras and so on, convey to an equal extent the different penetrations of the colored light in the atmosphere of Mars, the way red, green, and blue filters generally do. So I have a bias, I suppose. And, I'm an old man, and I learned from Don Parker, and so I go way back. And all I can say is, a lot of these young guys probably know more than I do.
Thanks, Roger. Thank you. You'll have to come up.
Thank you.
Thank you for that great presentation. In the movie The Martian, Matt Damon was stuck in a storm. Could you comment on that storm?
I really can't. We could have fun with that, but it's just not what I do.
Yeah, so I'm more of a beginner with imaging Mars, so I unfortunately have a color camera with bare images. Can I still at least get to see some cloud features, even though they may not be the best things to use?
Yeah, well, certainly. Yeah, you'll see them. And sure, and a lot of the good scientific data is obtained with color cameras, so I don't object to them at all. This is difficult to say, and I don't want to belabor, but I just think if you look at Damien Peach, to my knowledge, he's still using red, green, and blue filters. Well, I mentioned the name of Damien Peach. I can think of several other observers whose images are consistently better, believe it or not. I mean, I'm just going to tell you, they're better than those of most imagers, and not a one of them uses a color camera.
Yeah,
So I'm biased, and
Yeah, I haven't quite gotten it. I have one other question, it might be a dumb question. But I thought dust storms were red.
they look, let's call it ochre. Yeah, they look reddish. Most of the free dust on Mars is reddish, and when it's lifted from the surface, it tends to actually obscure dark rocks. And when it's on the surface, it doesn't sit on the rocks, it's in between them. And when the wind is strong enough to blow it out from between the dark rocks it's sitting between, it obscures them so you can't see the rocks in their dark color. And therefore the whole sky looks as bright as the red color, the bright red color of Mars. And so when you see a dust storm, it's actually brighter red than the bright red features of Mars, of the surface of Mars, you see? Have I explained that to you?
Yes, thank you.
Scott, do we have any online? No, there are no other questions. Check the other feed here. Well, we've got someone who just needs to be blocked online. Go ahead. Any other questions? So Roger, we don't have any other questions. Just want to thank you again for a very enlightening discussion tonight on things to look at, and how to look at them on Mars. And again, just thank you very much for presenting tonight.
I had an imager send me an image where he thought the North Polar Hood looked, quote, disturbed, unquote, or something like that. And I explained to him, hey, this is great. You've imaged a North Polar Hood cyclone, and, see how it's traveling southward and all this. And, boy, you don't want to be standing under that because it's windy and dirty, and all this stuff. And I told him we document these things all the time. Well, the point I want to make is that he didn't realize that his image was a valuable documentation of weather on Mars. He was sort of apologetic that it would be not what it was supposed to show. And, I'll know what it shows. You just send it to me. Okay? Go ahead and image your best images and send them to me, and we'll put it all together for you.
Great, thank you.
Great, thank you.
That'll conclude that part of the session. And so what I just want to make one last announcement before we close the meeting is just, if you hadn't seen, Telescopes for Kids again is on this year. Scott Young down in front is one of the people coordinating it. And there's also a GoFundMe page that's being sent up for those that wish to donate cash for us to be able to buy eyepieces and things like that. There'll be more information on the groups.io, and so just look for additional information. And right after the meeting, for those that are interested, at the Boston Pizza, just over on Pembina, there'll be a few people gathering over there for drinks and bites. And with that, meeting is all over. Thank you very much for coming up.
This is my friend Arlene.
Hi.
A few days ago, we were over at an old friend of mine, Lyle Frank, and he was talking about a bunch of parodies that used to live at Dunray.
Yeah.
And that would be you.
Well, there's two families in Dunray. There was. I think there's one that's still there. They used to own the plumbing and electrical thing, and they have now. I think they're mostly situated in Brandon.
Oh, okay,
But
maybe
they have
that's who.
this,
Yeah.
thermal heating business.
Yeah, I think that's who he was talking about.
That's the other family.
Okay,
They're second. He was a second cousin to that.
okay.
Two different families
Yeah,
that came
yeah.
out west.
Yeah,
Asking them.
okay.
But my family, most of my family was in Startup, Saskatchewan. But my
Okay.
father pretty well grew up in Dunray among his mother's family.